Learning targets 5 and 6. We've actually talked about these a little bit already. Um, Basically, we're nearing the end of the unit, so we're going to take all the stuff we know about exponentials and then kind of fit them to some real-world context kind of stuff. Learning target 5 is just modeling an exponential equation to fit a context. We've done this quite a few times already if you think about the contagion, the Hercules example, and then the zombies and babies that we did on Friday. So we've done this quite a bit already, and then learning target 6 is just pretty simple, distinguishing between when something is an exponential growth and when is it a decay, which we also did on Friday. So if we look at exponential growth, remember if we're thinking about an exponential function, we've got our two pieces. We've got a, which is the starting value, and then we've got b, which is the multiplier. We talked about y, how that can stand for several different things. X is usually like the cycle or the per day or per year or whatever. So if we're looking at exponential growth, the value of b is going to be something greater than 1. Okay. If it's growing at a fixed percent, which is what we saw with the population growth of the Earth, we were able to calculate a fixed percent. Then our b value is going to be equal to 1 plus the percentage rate, which I'll say r. We'll say r is percent rate. So if it is growing by, we'll say 10%, then b would equal 1 plus 10%. And in this case, b would equal 1.1. So we would have b in our exponential equation as 1.1 if something is growing at a 10% rate. On the flip side, if we have exponential decay, the value of b is going to be less than 1. And if it's decaying at a fixed percent, then our b value, or our multiplier, is going to be 1 minus r. So as we saw with the zombies example, if we'll say 20% of the population dies each day, or 10% or whatever. In this case, we'll just say 20%. So our percent rate, r, is 20%. Then our b value, our multiplier, would be 1 minus 20%. And in this case, that would be 0.8. So our exponential equation would be y equals whatever our starting value is times 0.8 to the x. Okay. Example A, bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start with only one bacteria, which can double every hour, how many bacteria cells would there be after only 12 hours? Write an exponential equation, then use it to find the answer. So if we kind of think about this visually, we've got one bacteria, and this would be like our cycle 0. After 1 hour, this bacteria splits in 2 and it doubles. So this would be 1 hour. And the next hour, each bacteria doubles, splits itself again. So now we're at 2 hours. And it's going to split. They're all going to split into 2 again in the next hour. That's hour 3. So if we start to make a table for this, in this case, x represents hours, and y represents total number of bacteria. So we've got a cycle of 0, 1 bacteria. After 1 hour, we've got 2 bacteria. After 2 hours, we've got 4. And after 3, we've got 8. Okay, so as you can see, this is doubling each time. So when we go to write our y equals ab to the x equation, our starting value is 1 bacteria. It's doubling, so our multiplier is 2, and then we'll take that to the x. Now, go back to the question. So the question is asking us, after 12 hours, how many bacteria will there be? Okay, so if we need to calculate this for 12 hours, we need x to be 12. So we're looking at y equals 1 times 2 to the 12th. Okay, so we'll figure out 2 to the 12th. 2 to the 12th is 4,096. Okay, so we've got y equals 1 times 4,096, which is 1 times 4,096 is just 4,096. So after 12 hours, there are 4,096 bacteria. Example B, after you drive a car off the lot, it decreases in value by about 20% each year. Let's say you buy a new car that is $16,000. Write an equation to represent your new car's value over time and use the equation to find out what it will be worth in 5 years. Okay, so we start with our $16,000 car. And each year it loses 20%. So since it's losing 20%, we're looking at an exponential decay type equation. Okay, if we were going to graph this, we'd be up here starting at 16,000 and each year going down 20%. So our graph of this would look somewhat similar to that. So then if we're going to start to write an equation for this, y equals a times b to the x. The a is fairly obvious in this case. It starts being worth $16,000 times b to the x, and now we need to figure out what our b value is. Since this is an exponential decay situation, this is going to be 1 minus r, and we are decreasing, so that's where we get the minus from, because this is a decay sort of situation. The car is becoming less valuable each year, and it's becoming less valuable by 20%. So our b value is going to be 1 minus 0.20, which in this case is 0.8. So that's our b value. So we've got y equals 16,000 times 0.8 to the x. And let's define our variables really quick. So y in this case represents the value of the car, and x represents how many years old it is. So for each year after you buy it, it loses 20%. So x is the number of years after you've bought it, and we're looking for, we're looking for how much it will be worth in 5 years. So that means that our x value is going to be equal to 5. So right here for x, I'm going to put in 5. We're going to get y equals 16,000 times 0.8 to the 5th. I don't know what 0.8 to the 5th is off the top of my head, believe it or not. So 0.8 to the 5th is 0.32768. So down here we've got 16,000 times 0.32768, which is about $5,242.88. And that's how much the car will be worth after 5 years. So before class, Johnny puts $100 into a savings account. has an interest rate of 4% and left it alone in the account for 12 years. Determine if this is an exponential growth or decay, and then write the equation. Use